Another problem that you encounter in the homework, actually 2 times, is the bar launcher. So let's take a look at that problem and see what's the approach for that problem. So what you have there is a cable, U-shaped, but you put a resistor here to make sure that the current doesn't go to infinity, and you put a battery here, and you get the polarity of the battery. So you get the battery here like this. This is the positive side, this is the negative. The battery has some EMF E, and you're going to place a bar there that can slide. We're assuming that there's not going to be any friction acting on that bar. The resistor has resistance R. Maybe it's the battery that has some internal resistance. So as soon as you turn on, you connect the battery to the circuit, there will be a force on that bar. How do we know that? The current on this circuit is going to flow from positive. Initially, it's going to go from positive to negative. So the current flows like this and down the bar, back to the battery, correct? So that's the direction of the current that flows through the bar, the sliding bar that we have placed there. If a wire has a current and it is in a magnetic field, and I haven't shown you what's the direction of the magnetic field yet, I think it's going into my example. That's your B. Let's say that the bar has a length L. Then there will be a force on that bar because wires carrying current in a magnetic field experience a force, just like the jumping wire demo showed you that that's the case, right? So what's the direction of the force on that wire? Use your right hand. Because we're asking for force, you're going to put it either with the 3 fingers sticking out or just your open hand flat, either whichever is your preferred one, right? You put your thumb in the direction of the current, you put your index in the direction of the magnetic field, and you end up with your middle finger sticking to the right. So that is the direction of the force on that bar. So as soon as you close the switch, if there was a switch here, the bar would start moving to the right. How much is the force on that bar? The force on the bar is equal to, if you remember this equation, I delta L cross B. Since delta L and B are perpendicular to each other, this is simply I delta L B. Delta L is the length of the segment of the wire that you're considering. In this case, is the bar, the one that we're looking at the force on it. So your delta L is simply L. So I, L, B, and the direction, we just figure it out. It's to the right. That is the force that is accelerating the bar, and it's due to the fact that the bar has a current, and it's moving in a magnetic field. Now, what's going to happen later? I mean, initially the bar is stationary, then it starts to move. What's going to happen as soon as the bar starts to move? There is a second effect that kicks in this problem. What am I talking about? What is the second effect? Right. There will be an induced current, an induced electromotive force across the bar or in the circuit that the bar is making. Why is that? Because the bar and the cable define a circuit, and as the bar starts to move to the right, that area starts to grow. And if the area of the circuit grows, even though the magnetic field is not changing, your flux grows. Right? So as the bar moves to the right, your flux starts to increase. So the flow increases. The flow is in the circuit is in the direction of the magnetic field pointing into the page. If the flux increases in that direction, there should be the tendency of the circuit to produce a magnetic field that opposes that change. Right? So the bar will turn into an electromotive force that tries to push current in the direction such that it would oppose the change in flux in the circuit. So what that means is that the induced magnetic field in this circuit will be pointing out of the page. Right? This is the induced direction of the induced magnetic field. So to induce a magnetic field that is coming out of the page, the current that the bar wants to push through the circuit is this way. Right? Now the EMF that develops across that bar is given by the change in flux with respect to time. And the direction of that current, the direction of the EMF is going to be like this. This side of the bar is going to turn into positive. This side of the bar is going to turn into negative because it wants to push current in the direction that is counterclockwise, opposite to the direction that the battery is trying to do. Right? Now, how do we figure out how much is the EMF that develops across the bar just because the bar is moving to the right? Well, we just simply use the definition of the flux. This is going to be B. In this case, B is constant, so the derivative is only going to apply to the area. We do know the area is changing. It is actually growing because the bar is moving. What is the change in the area? Well, at any given time, the area is going to be given by L multiplied by, if you want to call this distance x, you're welcome to do that. And the derivative of that will be dx dt. So the EMF that develops across the bar, it's going to be equal to B, L, dx dt is the velocity of the bar. So here's a sort of a simplified or schematic view of what's going on in that circuit. So I'm going to replace the bar with a battery, sort of a battery, because it has an EMF that we just calculated, is BLV. So the bar is going to act like a battery, and we figure out in which direction that EMF is going to act, right? So the bar is going to have polarity like this. And this is BLV, and this is the positive side, and this is the negative side, right? The bar wants to push current counterclockwise. The battery wants to push current this way, right? There will be a single current, obviously, in your circuit. There cannot be two different currents, right? So what you do is, since you have now two sources of electromotive power, you just do the usual loop, Kirchhoff's loop law, move around the circuit, and see what you get. So the terms that you're going to write when writing Kirchhoff's loop law is you move across the battery, so that's the EMF of the battery. You're going from negative to positive, so that's a plus. You move through a resistor, that's a drop in potential. Now you move through the second EMF. Remember that we're walking this way, right? So now you're moving from the positive to the negative side. So that's a drop in potential again. You're going to lower ground. So that is this EMF of the bar that we calculated as BLV. And you're back to the original point, which was here. So this should be equal to 0. So that equation tells you how much is the current in the circuit, right? You can solve for the current there. You can say that the current then is going to be the EMF of the battery minus the EMF of the bar divided by the resistance in the circuit. But notice that that EMF of the bar depends on the velocity. It's right here. So when the velocity is 0, the current in the circuit is just epsilon divided by R. It's just what the battery is putting out, epsilon divided by the resistance, that's your current. But as soon as the bar picks up some velocity, the EMF of the bar starts to grow because it's BLV. As soon as that grows, then E minus E of the bar is decreasing. So the current flowing through the circuit is decreasing. All right? And there's going to be a point, but the current in the circuit is decreasing, but as far as you have a current, you have a force pushing on that bar. And if you have a force pushing on that bar, there is an acceleration acting on that bar. So that what I'm trying to say is that as long as there is a current flowing in the circuit, your bar is going to be accelerating and your velocity is going to be growing. Right? So this term grows continuously, which makes epsilon minus that term decrease continuously. And there's going to be a point when the current flowing through the circuit goes to 0. when this equals this. And you will get to that point, because the velocity is going to grow as much as it can, and the term BLV, which is starting from 0, it's going to reach eventually the value epsilon. When it does that, the current is going to be 0. The current flowing in your circuit is going to be 0, which means the force on the bar is going to be 0. That's when the bar stops accelerating. It's just reached terminal velocity, and it continues to move with that velocity if there is no friction, for as long as there is a magnetic field acting on the bar. Okay? So that is why this bar is going to reach terminal velocity. That's as described by that equation.